Okay, so we've talked about spanning sets, and we know that if we have a spanning set, we can express a vector as a linear combination of the vectors in the set, in the spanning set. And it turns out that this spanning set gives us a nice way of representing vectors. So we'll see how that works out. All right, consider this spanning set. Let's look at an example first. Let's consider this spanning set. And it turns out that these vectors form a matrix whose columns are the matrix is non-singular, so that means these are linearly independent. And in fact, these columns span all of C3. In fact, any vector B can be expressed as any vector B can be expressed in the form AX is equal to B. We can always find a solution, and what that means is that B is a linear combination of the columns of A, where you have x1 times the first column plus x2 times the second column plus x3 times the third column. Okay, so let's go on with this particular choice. B, since S is a spanning set for C3, we can actually write B as a linear combination. It turns out that the result is this. And in fact, since the matrix A is non-singular, it means that there's only one linear combination of the vectors in this spanning set that gives me the vector B. All right, so that's the key point here, is you have these vectors here that are linearly independent, these spanning vectors that are linearly independent, and if I take any vector in their span, there's a unique way to write this vector as a linear combination of the vectors in S. So that means there's only one representation. This is very useful. When you have unique representations, this is always very useful. You know, with ordinary numbers, I can represent 24 as in its prime factorization. It's equal to 2 times 2 times 2 times 2 times 3. And that's unique. There's only one way to write it as a product of prime factors. Here we have a way to represent a vector uniquely as a linear combination. That's something very important that we'll be using later. Okay? So we're going to encapsulate that result in a theorem. And here's the theorem. Suppose that V is a vector space and B is a linearly independent spanning set for V. So linear independence is very important. All right, so that means there's no non-trivial linear dependence relation between them. Let V be any vector in this vector space V. Then there exists a unique scalars such that that arbitrary vector in the vector space can be written as a linear combination of the vectors in the spanning set. Okay? All right, so we have to show two things. We have to show that any vector in V can be written as a linear combination. And we have to show that any vector in V can be written as at most one linear combination. There's only one linear combination that works. Now, the fact that any vector can be written as a linear combination simply follows from the fact that B is a spanning set. So that's easy. All right, now we need to show that it can be written uniquely. So to do that, let's write V as a linear combination in two ways. And we'll show that, in fact, these corresponding constants must be equal. That, in fact, although we've written the coefficients in a variable way, the coefficients are uniquely determined. Okay, so let's write B in these two different ways, and let's subtract one equation from the other. That's basically what's going on here. We write 0 as W minus W. When you subtract one equation from the other, you'll end up subtracting the corresponding coefficients. So if I take this equation minus this equation, the first coefficient gives me A1 minus B1, second one gives me A2 minus B2, all the way up to AM minus BM. Okay? So here I have 0 is equal to this linear combination of the vectors V1 through Vm. However, we know that these vectors are linearly independent. The only possible way to get a linear combination of these vectors to be 0 is if every single coefficient in this linear combination is equal to 0. So we must have all of the coefficients equal to 0, which gives us, in fact, the coefficient a1 is equal to b1, coefficient a2 equal b2, a3 equal b3, all the way up to am equal bm. So these are all unique. Okay, so this is a very nice result. This is so nice that when we have a spanning set that's linearly independent, we give it a special name. It's called a basis. And it's a basis because it's a basis for expressing all the vectors in the vector space. So we'll talk a lot about bases in subsequent sections.